So yesterday we looked at what the graph of a radical function looks like. We did transformations on that base graph, y equals root x. So today we're going to see what happens when you have an original function and then you take the square root of that function. So it doesn't start as a radical, but you're going to make it a radical by taking the square root of it, and we'll see what effect that has on the original graph. So this will be another type of transformation. So again, we're going to sketch the graph of y equals the root of f at x given the graph of y equals f at x. We'll talk about some strategies for graphing the square root of a function, and we'll compare the domain and range of the two. So we can determine how two functions y equals f at x and y equals the root of f at x are related by comparing how the values of y are calculated. So if you start with the function y equals 2x plus 1, you can see the table of values here for some specific values of x. When x is 0, 2 times 0 is 0, plus 1 is 1, 2 times 4 is 8, plus 1 is 9, and so on. So those will give you the values for y equals 2x plus 1. And then if you're going to take y equals the root of 2x plus 1, as you can see in the table, you simply take the square root of all the y values. Right? For y equals 2x plus 1, when x is 0, y is 1. Well, that point on y equals the root of 2x plus 1 would actually be the same point because the square root of 1 is still 1. But these other points are different because the square root of 9 is 3, the square root of 25 is 5, and so on. So essentially, you're taking the square root of all the y values. But one major difference is that for y equals the root of f at x, it's only defined for f at x, meaning what's under the radical being greater than or equal to 0, because you cannot take the square root of a negative number. So there are those restrictions. So this example says, given f at x equals 3 minus 2x, graph y equals f at x, as well as the square root of f at x, and compare the two functions. Then we're going to algebraically determine where the invariant points are and also state the mapping notation. All right? So the graph of y equals 3 minus 2x. If we put that in slope-intercept form, it would be negative 2x plus 3. So that would be a line. It's a line with a y-intercept of positive 3 and a slope of negative 2, which we talk about in terms of rise over run, negative 2 over 1. So you rise negative 2 and run 1. Rise negative 2 and run 1. We could also rise positive 2 and run negative 1. That would work as well. But this is the graph of that linear function, negative 2x plus 3. Now, if we want to graph the square root of that function, as we saw, we would take the square root of the y values. We also said that that function would only be valid when f at x is greater than or equal to 0. So if I highlight the portion of the graph that would not be used for the second part of this, the square root function, it would be that portion there. Because anywhere to the left of the y-axis, I'm sorry, that's completely wrong. It should be down here, where f at x is negative. So anywhere down there, the square root function will not be valid, because there the values of y are negative, and you cannot take the square root of a negative number. But we can take any other points on the line, look at the y values, and take the square root of those y values. So let's do that. Let's start with this point right here, the x-intercept, which would be at positive 1.5. We could get that by letting y equals 0 in the equation and solving for x. But the value of y there is 0. And the square root of 0 is still 0. So this will actually be an invariant point. That point right there. We'll have another invariant point right here where y is 1. Remember, you're taking the square root of all the y values, and the square root of 1 is 1. So that point will be on the graph of the square root function. Maybe I'll change colors here. Okay. If I take this point here, which was the y-intercept of the original graph, the value of y there is positive 3. So the corresponding point on the square root function will be the root of 3, which is, I think, approximately 1.7. The root of 3, yeah, 1.73. So this point here, where y is positive 3, becomes 1.73. Let's take one more point. This point up here where y is positive 4. We don't know exactly what the x value is, but the y value is 4. And the square root of that is 2. So the point on the square root of this function will have the same x value, but now the y value will be positive 2. Approximately right there. Here's what the graph will look like. It'll look something like this. Right? This is a square root function. So we saw yesterday what the graph of the square root function looks like. This is the graph of y equals the root of negative 2x plus 3. And we can write that equation in a format where we can talk about transformations by taking out a common factor of negative 2, because remember, in this case, we're going to have a b and an h value. Our b value is negative 2, but the h value is not negative 3. To get the true h value, b must be taken out as a common factor. And we did this back in chapter 1. So if we want to look at this equation and talk about it in terms of a transformation of y equals root of x, this is what we would do. We would say that the graph compared to y equals root of x has been reflected over the y-axis because b is negative. It's been horizontally stretched by a factor of a half, because remember the horizontal stretch factor and the b value are reciprocals of each other, and it's also been moved 1.5 units to the right. So we can talk about this graph in terms of a transformation of y equals root x as well. But this is what the graph looks like. Now, there are two invariant points here. The invariant points are where y is 0, because the root of 0 is still 0, and also where y equals 1, because the root of 1 is still 1. And in part C, it asked us to algebraically determine the invariant points. The invariant points for the square root of a function will always be where y equals 0 and y equals 1. And because they're invariant points, they're on both equations. They're on the original equation and they're on the new equation. It's much easier to work with the original equation in this case because it is a linear function. So we can algebraically show where those invariant points is or are by finding where negative 2x plus 3 equals 0 and also where negative 2x plus 3 equals 1. Because that's where our invariant points are, where y is 0 and also where y is 1. So if you subtract the 3 from both sides, you'll get negative 3 on the left, equaling negative 2x. And then when you divide both sides by negative 2, we'll get x equals 3/2 or 1.5. So that was the x-intercept. The x-intercepts are invariant. The points where y equals 0 will give you one set of invariant points. And y equals 0 is where the x-intercept is. But also where negative 2x plus 3 equals positive 1. So if you subtract the 3 from both sides, you'll get negative 2 on the left. And then divide by negative 2, you'll get x equal 1. That is the point 1, 1. So 1, 1 is one invariant point. 3/2, 0 is the second invariant point. So we found those points on the graph, and then we algebraically determined them just to confirm them. So there's our invariant points. Our mapping notation would be x, y maps into x, the root of y, because that's what we did. We took the square root of all the y values from the original function. Okay, so if we're talking about comparing the two functions, there are some similarities. They do share 2 points, but there's a lot of differences as well, right? The first one is a linear function. The second one is a radical function. The domain and ranges are completely different. The domain and range for the linear function are all real numbers, but the domain and range for the rational function are different, okay? So the domain of that rational function would be from negative infinity to positive 3/2. The range would be from 0 to positive infinity. And we have a square bracket on the 3/2 because it's included in the domain, a square bracket on the 0 because it's included in the range. The only similar characteristics of these two graphs are the invariant points. As well, they are both functions. But other than that, they're two completely different functions. Okay? So, here's how we graph the square root of a function given the original function. We start with finding the invariant points. The invariant points are where y is 0, which are the x-intercept or intercepts, and also where y equals 1. So that's where we're always going to start. Okay? We can find and generate some more points by taking some other random points on the original graph and taking the square root of the y values. That's what we did. The other thing I want to make note of is that between the two invariant points where y is 0 and y is 1, notice that the new graph is slightly above the old. But after the invariant points, the new graph will be below the old. Okay? And here's the reason why. Between the two invariant points where the value of y is between 0 and 1, it's going to be a decimal between 0 and 1. If we take the square root of any number between 0 and 1, for example, the square root of 0.5, that gives us a value that's greater than 0.5, 0.707, greater than 0.5. That's why the graph of the new function between 0 and 1 is slightly above the original, because the square root of any decimal between 0 and 1 will give you a number greater than what you started with. If we took the square root of 0.75, that's between 0 and 1, again, we get a decimal greater than 0.75. If we took the square root of 0.25, again, that's between 0 and 1, we get a decimal greater than 0.25. This is the reason that between the invariant points where y is between 0 and 1, the new graph is slightly above. The square root of any decimal between 0 and 1 will be a decimal greater than what you started with. So the graph is slightly above the original. But after that, the square root of 3 was 1.7. That's less than the number you started with. The square root of 4 is 2. Again, that's less than the number that we started with. So this is the reason that the new graph is below the original once you get past the two invariant points. So we start with the invariant points where x is 0, where y is 0 and where y is 1. We know that between the two invariant points, the new graph is slightly above the original. After that, the graph will be below the original, and the graph will also be a curve of some kind because it's going to be a square root function. Okay? We're going to see that not all of these will have this general shape that we looked at yesterday that we see here. It depends on what the original function is. And so we'll look at a bunch of different examples. But basically, that's how you graph the square root of a function. So in this case, we're going to start with the graph of y equals 3x plus 6. So that's a linear function that has a y-intercept of 6 and a slope of 3 or 3 over 1. Now we don't have room here to rise 3 and run 1, but we can rise negative 3 and run negative 1. That'll work. Rise negative 3 and run negative 1. That works. So this is the graph of the original function. It's a linear function. And now we want to graph the square root of that function. And we start with the invariant points. The invariant points are where y is 0, and there's one of those, and also where y is positive 1, and there is one of those. We don't know exactly what the x value there is, but we don't need to know exactly where the x value is. We can see on the graph where y equals 1. We could generate a couple other points here, maybe one specifically where y is positive 4. The square root of that is 2. So the x value won't change. This point will be directly below the original point where y equals 4 because the x value doesn't change, but the y value does because the square root of 4 is 2. Remember, between the two invariant points, the new graph is slightly above the original, and then after that it goes below. And this graph will have that same shape of what a square root function looks like. It will be that curve. So there's the graph of the square root of that function. We can algebraically determine where those invariant points are by finding on the original equation where y equals 0 and where y equals 1. So if you subtract the 6 from both sides and divide by 3, you'll get x equals negative 2. This is where y equals 0. So the point negative 2 comma 0 is invariant, which we have on our graph. That's where we started it. But we also have an invariant point where y equals 1. So if we solve the linear equation when y equals 1 by subtracting the 6 from both sides and then dividing by 3, we get x equals negative 5/3. That is the point negative 5/3 comma 1. So we could see on the graph where that was, but we didn't know what the x value was there until now. Okay? Identify the domain and range of each function. So let's do that. So for g at x equals 3x plus 6, the domain and range are both all real numbers or from negative infinity to positive infinity. But for our rational function, for the root of 3x plus 6, the domain and range are different. The domain would be from -2 to positive infinity. The -2 is included. And the range would be from 0 up to positive infinity. Remember, the radical function is not valid when f at x is negative, when the original graph is below the x-axis. You will not get values for the square root function because you cannot take the root of a negative number. And remember, we're taking the square root of all the y values, so it won't work where y is negative. The mapping notation, same as what it was on the previous question. You're taking the square root of all the y values. So there's the mapping notation. Okay, so here's a summary of what we've just talked about. The domain of y equals the root of x, root of f at x, consists only of the values in the domain of f at x for which f at x is greater than or equal to 0, meaning y can't be negative. The range of y equals the root of f at x consists of the square roots of the values in the range of y equals f at x, where the root of f at x is defined. The graph of the square root function exists only where f at x is greater than or equal to 0. Again, that's saying that only where y is greater than or equal to 0. It can't be negative. You can predict locations of y equals root of f at x relative to y equals f at x using the values of f at x. Again, that means using the y values and taking the square root of them. When f at x is negative, that means y is negative. The graph of the radical function is undefined. When f at x equals 0, that will be an invariant point. They intersect on the x-axis. When f at x is between 0 and 1, remember that the graph of the radical is slightly above the graph of f at x. When f at x equals 1, that'll be our second set of invariant point or points. And when f at x is greater than 1, now the graph of the new one is below the graph of the original. So really, this gives us the steps that we can follow in order to sketch the square root of a function from an original. So let's look at these two examples. The first one being y equals 2 minus 0.5x squared. That's the same thing as y equals negative 0.5x squared plus 2. That means it's the graph of y equals x squared that undergoes some transformations. The value of a is negative 1/2. So it's going to be reflected over the x-axis, and also it will be vertically stretched by a factor of 1/2 about the x-axis. Also, it'll be shifted up 2 units. So instead of having a vertex at 0, 0, it'll have a vertex at 0, 2. And the graph will open downwards. Now, we can find where the x-intercepts are by letting y equal 0. If you let y equal 0, you can find out where those x-intercepts are. And on almost every diploma exam, there'll be a question where you have to find either the x or y intercepts for some function. The x-intercepts are always where y equals 0. The y-intercept is always where x equals 0. So if we add the 0.5x squared to both sides, it'll become a positive on the left side. When you divide both sides by 1/2, 2 divided by 1/2 is 4. And then when you take the square root, and we're solving an equation, there's always two answers, the positive and the negative. So plus and minus 2 are where the x-intercepts are. So this is what the graph of the original function will look like. Now, to graph the radical function, we have some invariant points here. The first set of invariant points are where y equals 0, the x-intercepts. There are two x-intercepts on the original graph. So there's two invariant points from those points. But also where y equals 1. There are two of those points as well. Let's find one more point. The vertex of the original graph is where y equals 2. The corresponding point on the radical function will be where y equals the root of 2, which I think is about 1.4. Yep. So 1.4 is approximately there. Remember, between the two invariant points, the radical function is slightly above the original. After that, it's below. Between the two invariant points, the graph is slightly above. After that, it's below. Let me try that one more time. I want to clearly show that the new one is slightly above the original between the invariant points. There's our graph. So this one looks completely different from the radical functions that we have been working from. And it's because of the nature of the original function. The original function was a quadratic. So if we algebraically determine where those invariant points are, using the original graph or original function, 2 minus 0.5x squared, they are where y equals 0 and also where y equals 1. But let's solve this one first. If you add the 0.5x squared to both sides, divide both sides by 0.5, and in fact, we actually already did this when we found the x-intercepts of the original graph. This is what we did. So the invariant points were at plus and minus 2, 0. But we also have a set of invariant points where y equals 1. So now if you subtract the 2 from both sides, 1 take away 2 is negative 1. And we still have negative 0.5x squared on the right side. If you divide both sides by negative 1/2, 1 divided by negative 1 divided by negative 1/2 will be positive 2 equals x squared. And then x will equal the positive and negative root of 2. Again, when you're solving an equation and you take the square root of both sides, there's always the positive and negative. And this was where y equals 1. So those two invariant points are at positive and negative root 2, positive and negative 1.4 approximately, 1. Okay? And again, the mapping notation is always the same for these. We're taking the square root of all the y values. Right, so again, this graph looks completely different than all the other radical functions we've looked at because the original function is a quadratic, not a linear, which is what we dealt with yesterday. The original functions were linear, or the radicand was linear. All right, what about y equals x squared plus 5? So that's the graph of y equals x squared shifted up 5 units. You're going to have a vertex up at positive 5. And the graph will go up to the right and up to the left. Dylan, where are the invariant points for this? Right? Say again? That's right. There are no invariant points for this one. The invariant points occur where y equals 0 and y equals 1. That doesn't happen here. So there are no invariant points. But we can still take points on the original graph and take the square root of them. So let's start with the vertex where y is 5. The corresponding point on the new graph will be the root of 5, which is 2.24. Remember, the x value doesn't change, it's 0, but the y value will change. It again is the root of 5, which is 2.24. So that would be approximately there. Let's take this point and this point, which was where y was 6. The square root of 6, we can do on our calculator. It's approximately 2.2449. A little bit more than the previous value of 2.236. A little bit more. The x values don't change, but the y values are slightly higher. And remember, once we get past the invariant points of the original graph, the new graph will always be below the original. So this graph will always be below the original. It would look something like this. And don't forget, you can always use your graphing calculator to see what this looks like. If we start with the original equation, x squared plus 5, and then we graph the square root of that, zoom 6 to set my windows to their standard settings, that's what it looks like. So there are no invariant points, and we can show that algebraically by letting x squared plus 5 equals 0. If you subtract the 5 from both sides, you'll get negative 5 on the left. And when you time take the square root, can't take the root of negative 5. So there are no x-intercepts there. And where we let y equal 1, the same thing's going to happen because you're going to get a negative value on the other side when you subtract 5 from both sides. So we're showing algebraically that there are no invariant points because there's nowhere where the original graph equals either 0 or 1. And the mapping notation is the same. Okay? So now we're going to work with the base graph x squared minus 1. That's the graph of y equals x squared shifted down 1 unit. Instead of having a vertex at 0, 0, it'll be at 0, negative 1. Instead of going through negative 1, 1, it'll shift 1 unit down. 1, 1 shifts 1 unit down. Negative 2, 4, and 2, 4 shift 1 unit down. So this is the graph of x squared minus 1. And now we want to graph the radical function, the root of x squared minus 1. Vish, do we have invariant points here? Where? Huh? The point minus 1, 0 right there. Okay. Any other invariant points? Is that it? You want to bet a pop on that? Huh? Yes or no? Sure. Is he right? There's two more actually. The invariant points occur where y equals 0 and also where y equals 1. I like Coke fish. And make sure it's ice cold. And none of this Superstore crap either. I want the original. So we have four invariant points. Two places where y is 0, two places where y is 1. Remember that where the original graph is negative, which is between -1 and +1, we will not have any points on the radical function. Remember also between the invariant points, the new graph is slightly above the original. After that, it's below. Same thing's going to happen on both sides. Between the invariant points, the new graph is slightly above. After that, it's below. So that's what the graph of the radical function looks like. If we compare the domain and ranges for y equals x squared minus 1, the domain will be from -infinity to +infinity. The range will be from -1 up to +infinity. But for the radical function, the root of x squared minus 1, the domain will have to be in two parts. It'll have to be from -infinity to -1, which is included. And so this upside down u essentially is what it is. It's part of set notation. It means and, or intersection. Okay? And the second part of this will be from +1 to +infinity. The range would be from 0 up to +infinity. Right? So we assumed, well, we didn't assume, we found out that the point -1, 0 and 1, 0 were the x-intercepts of the original graph. So we didn't assume that. We found that by transformations. But we can algebraically determine where those invariant points are, at least the two x-intercepts, by solving x squared minus 1 equals 1 and x squared minus 1 equals 0. So these are our invariant points where x squared minus 1 equals 0, because the invariant points occur where y equals 0 and also where y equals 1. So we let it equal 0 first, solve for x squared, add 1 to both sides, and then take the square root. There's where you get your plus and minus 1. Plus and minus 1, comma 0 are our first set of invariant points, and our second set will be where y equals 1. So here, if you add the 1 to both sides and take the square root, you'll get x equals plus and minus root 2. It's always best to use exact values. I mean, that is approximately 1.4, but it's always best to use exact values. So this was where y equaled 1. Okay? We've done the mapping notation. It's no different. X comma y maps into x comma root y. And we can verify our answers by graphing it in the calculator. So the original equation was x squared minus 1. And now we're taking the square root of x squared minus 1. So the calculator in the current mode we're in almost shows the new graph to be straight lines, but it's not. If I go zoom decimal, I think you'll see a little bit better, actually, a little bit better. You can kind of see that here the new graph is slightly above the original, and same thing over there. If we reduce the y maximum even more, we might see it better. So let's use a y minimum of -1 and say a maximum of 3. You might get a better picture of it. Okay, so we can use the calculator to confirm. We can also find our points of intersection. Second function trace, remember that's where invariant points will be. So the second curve right now, it's at x equals 0, and there is no y value displayed because the second graph is not valid when x equals 0. It's only valid when x is greater than 1 or less than -1. So I'm going to have to move over until I start to see a y value. There we go. And it gives x equaling 1.414, which remember is the root of 2. Okay. So we can use the graphing calculator to confirm that our graph is correct. So in the examples we've looked at so far, we were given the equation of the original function. We had to graph it and then the square root. Sometimes, though, you'll just be given the original graph and you want to graph the square root function. So it's as simple as finding the invariant points where y is 0 and y is 1. In this case, there's only one place where y is 0, only one place where y is 1. We can generate at least one more point here. Let's take the y-intercept of the original graph, which is 4. The square root of that is 2. Remember, between the invariant points, the new graph is slightly above the original. After that, it'll be below. So there's the graph of the radical function. For the second one, we have 4 invariant points, 2 where y is 0 and 2 where y is 1. Between the invariant points, the new graph is slightly above. After that, it's below. We could, if we wanted to, be a little more accurate by, and let's do that. Take the square root of 4. That's 2. X values don't change, but the y values do. Square root of 4 is 2. This just gives us a more accurate sketch. Okay? So for this one then, we want to sketch the square root function. We have an invariant point where y is 0 and an invariant point where y is 1. This point way over here, the value of y is 4. The square root of that is 2. Between the invariant points, the new graph is slightly above. After that, it's below. So there's the graph of the radical function. Okay, so there's a summary of what we've talked about. And there's an assignment there that you can work on after. I will post the solutions to Google Classroom so you can check your work. I strongly encourage you to do that. We only have one more lesson in this chapter. It's a short chapter, so that'll be tomorrow. And then Monday, you guys will have a quiz on chapter 2. We'll start chapter 3 first, then you guys will write your chapter 2 quiz after. You should have received an email this morning about that your quiz is Monday. Okay, but we are going to go through your chapter 1 quiz.